Cool. Good morning. So we're going to start the lecture 14.3, where we're going to discuss mostly about the applications of the sound in medical purposes. So essentially, how we can measure the speed of the blood, for example, or its direction, or how we can measure the distances between the different objects and get the images in the medical purposes. And before we do this, we're going to again discuss about some principles, some physical properties of the sound. So last time we discussed about its frequency, its amplitude, and also we discussed about something which is called the Doppler shift, which essentially tells us that if the source of the sound is giving away some sound, and also it's moving towards this observer, then we're going to observe the higher frequency of the sound than its original one. And at the same time, if the sound is moving away from the observer, we are going to have moving away from the observer, then the frequency of the sound is going to be decreased. So you can see this in this image, that whenever we say about the frequency, it's the amount of the oscillation, the number of the oscillations per unit of time, so essentially per second. So originally the sound has some frequency. You can see here that it's having some frequency, and as its sounds move towards the person, its frequency is going to be increased, and if the sound is moving away from the observer, then its frequency is going to be decreased. So we've seen this example in this car, which is moving towards this observer, and as it moves towards this observer, its frequency is going to be increased. As it moves away, its frequency is going to be decreased. So last time, if you remember, there are two formulas which helps us to understand what are the frequencies and what are the velocities, and we are going to use them in order to understand a couple of things. So one thing, this principle, the Doppler shift, is used a lot in many applications, like in many spheres, and in engineering, or in astrophysics, or in medical purposes. So in engineering or in civil engineering, essentially, it is used when we are going to measure the speed of the cars using these radars, right? So when we are going to send some signal and we're going to get back the signal, and the frequency of the signal which we have sent and which we have observed as a rule is going to be different if the object is moving. And by just understanding what is this frequency difference, we can understand what is the speed of the object. So we've solved this problem in last time, if you remember. So let's try to solve this one more time. So essentially, I've got the sound source, which is coming from the train, right? From its horn. And the train is moving at a certain velocity. So the speed of the train, of the source, is equal to, say, 35 meters per second. And at the same time, that the speed of the sound, speed of the wave, essentially, right, is equal to the 331 meters per second if it is in the air. So at the same time, so I'm sitting in the observer. So if I know that the frequency of the sound, do you remember the frequency basically defines the tone of the sound, right? So this horn of the train may have the different tones. And let's assume that the frequency of the source is about 150 hertz. And I would like to understand what is going to be the frequency of the sound which I'm going to hear if the train is moving towards to me. Then I'm just going to put everything into this formula. So the F of the observer, yes.
The speed of sound wouldn't be 340.
Oh, it's written 340. Yes. Okay, sorry. But essentially, speed of the sound in the ear is 331. But like, depending on the temperature of the day outside, it may be a little bit more or a little bit less. Okay. At the 0 degrees Kelvin, it's equal to the 331. Okay, so let's take this 340. Then the F observer is going to be equal to F source multiplied to the 340 divided to the 340 minus 35. Could you please quickly calculate this? So I'm just going to tell you what is this. So I need to divide 340 to the 305, right? 340 divided to the 305 and multiply this to the 150. It's going to be 167.2. 167.2 hertz. So this is basically tells us that what is the frequency of the sound which we are going to hear if the train is moving. If the train stays, we're going to hear the same frequency essentially. So at the same time, if the observer now stays in the station and the train is moving away from the observer, and the train also is going to give away some sound, then we're going to hear the frequency differently. So the frequency of the observer is going to be the frequency of the source, the speed of the wave divided to the speed of the wave plus the speed of the sound. In this case, it's going to be 150 multiplied to the 340 divided to the 340 plus 35. And if you are going to put together all of the calculations, we're going to get 340 divided to 375 multiplied to the 150. It's going to be 136 hertz. Okay, did you understand like our calculations?
Yes.
Any questions about the calculations? Like if
No questions.
okay,
Professor,
so yes,
the first frequency is when the train is approaching, and the second one is when the train is leaving.
yes,
Yes.
yes.
Thank you.
The observer is not moving.
Yes.
Okay. So it has lots of applications, especially in medicine. It has applications when we would like to measure the speed of the blood and also its direction. So let's assume that you've got the vessels where the blood, for example, is moving in this direction or in this direction. So what you can do is you can just put some like transmitter or the reader. We call this as a transducer, which basically can give away some signal and it can also receive the signal. So let's assume that if the blood is moving away, then you're going to send some signal. You're going to send some signal and get back some signal. And the frequency of the signal which you're going to get back is going to be smaller than the frequency of the original signal, right? Because the object is moving away from you. Okay, do you understand? Do you understand me? So this frequency is going to be different. At the same time, if the object is moving towards the transducer, you're going to get some signal, you're going to send some signal, you're going to get back some signal. So let me draw this with different colors. So you are sending some signal towards the blood, and then you're going to get back the signal with the less frequency, right? Do you remember whenever we talk about the frequencies in terms of the colors, the blue color is going to have the higher frequency than the red color, right? So you're sending with the signal with the higher frequency, and you're going to get back this using the lower frequencies. If it is so, it means that the blood is moving away from the transducer. At the same time, if you are going to send some signal to the blood and you're going to have the higher frequency, it means that the blood is moving towards the transducer. So the Doppler shift is very helpful for us to understand the direction of the blood, where it goes, and also it helps us to understand what is actually the speed of the blood. Again, by just putting everything to the previous formula, we can calculate the speeds, right? Do you remember that we have got this formula? F observer is equal to the Fs V source V wave divided to the V wave minus or plus source, right? V source. You can find a V source from this formula actually easily, right? And then you can just calculate what is going to be the speed of the blood and also its direction. So it is especially very helpful when we are going to test some some cardiac issues. And also, it is very helpful when we are going to test the blood circulations of the babies when the women are pregnant. So you probably have heard about like Doppler screening. So it is about like measuring this everything about the blood circulations. It basically measures the direction of the blood and also its speed. So let's do a small example. So ultrasound that has a frequency of 2.5 megahertz is sent toward blood, and the artery that is moving towards the source at a speed of 20 centimeters per second. Use the speed of the sound in human tissue to be equal to the 1,540 meters per second, and find a frequency that so the blood receive. Find a frequency that returns to the source, and what beat frequency is produced at the source and returning. Okay, so we didn't learn about the beats yet, but could you please try to answer to this question? So what is going to be the frequency of the source which is returned to the source? Did you understand again the question? So here's the transducer. We're going to put this like to the direction of the artery where the blood is moving towards the transducer. So there is some signal is sent at the frequency of the 2.5 megahertz. And I would like to know what frequency I'm going to observe. Okay, what is the frequency of observed? Could you please calculate this? The formula is going to be like this. The frequency of observed is going to be equal to the frequency of the source multiplied to the speed of the wave divided to the speed of the wave plus or minus the speed of the source. So you put plus if the source is moving away, if the source of the sound or if the source of the signal is moving away, and you're going to put the minus if it moves towards to the source. Could you please calculate this, please? So should I put minus or plus? What do you think?
Minus.
Yeah, because it is moving towards to the transducer, right? Okay, so I'm just going to put minus, then it's going to be equal to the 2.5 megahertz multiplied to 1,540. It's the speed of the sound in the human tissue. So depending on the matter, the speed of the sound is going to be different. Divided to the 1,540 minus 20. Oh, by the way, 20 centimeters per second. What is going to be this in terms of the meters per second? So the 20 centimeters per second, it's like 0.2, right? Like meters per second, isn't it? Yes or not?
Yes.
Yeah, 0.2. Okay, let's calculate this. So 1,540 divided to the 1,538, and I have to multiply this to the 2.5. It's going to be 2.503. 2,503,000 hertz. Okay, but as a rule, so in this example, actually, so it was easy for us to calculate the frequency because we put everything into this formula. But as a rule, in practice, we are not interested in finding the frequency of the sound, or I mean, like calculating the frequency of the sound, because we can measure this, right? So this device, which is called a transducer, is going to be able to send some signal, and also it's able to receive some signal and tells us what is the frequency of the signal which came back. And by just knowing the initial signal and by just knowing the signal which came back, we can understand what is the speed of the blood which is coming towards or which is going away from the transducer. So it is very important application, especially in medicine. And one of the really cool applications of the Doppler shift was observed by Edwin Hubble. So there is a space space shuttle, which also is called by the name of the American physicist. He basically observed, or like experimentally observed, that the universe is expanding, right? So essentially, he has shown that the stars, which are moving away from the Earth, are giving the signal, the frequency of which is lower, right? So do you remember? So if some object is moving away from the observer, then the frequency is going to be decreased. So that is why sometimes we call this as a red shifted, because, like, as you know, the red color is going to have the lower frequency than the blue color. The blue color is going to have the higher frequency. And whenever the object is moving away, it's going to give us the red shifted frequency, because the frequency of the signal which we're going to observe is going to be smaller actually than the original frequency. So he has observed that the signal which we're getting from the stars actually is shifted towards to the red. It means that the objects are moving away. And also he shows that the more far away the objects are, they are moving far away, even more far away, they are expanding even faster. So essentially, this Doppler shift is telling us not only the direction of the object, which is moving towards to us, to the observer, or away from the observer, but also the speed. So especially for the blood, or especially for the space as well. And this was very important observation, because it was one of the proofs or evidences that the whole universe was created by the Big Bang Theory. So it started from the small thing, and it's expanding, nowadays as well. So I wanted to discuss with you the beat. So if you are going to have time, we're going to do this as well. So essentially, the beat is about like putting the two signals with the same the amplitude to the different with the different shifts. Or let's try to do this. So someone is writing in the chat. Oh, maybe yes or maybe not. This system can be trusted. Yeah, so actually you don't need to write your ID. So you can trust my system. So do you know, like, every time when you write down your ID into the chat, then professor should like go to the chat and check like every ID which has been written. But at the same time, it is possible to get like your information. If you logged into the Zoom, it tells me that when you have logged in, how much time you have logged in, and all of this information. So I can easily get this from the Zoom, and I usually do the attendance by using that information. Like, you need to be in the lecture, the amount of time, like at least 30 minutes, so that you are going to be marked as attended. Just a moment. Okay, do you see my screen?
Yes.
Okay, let's try to play with. So essentially, the meaning of the beat is when we are going to create the two signals. Like, okay, let me show it. So this is a GeoGebra, so you probably have seen this before. So you can just type the sign of x. Okay, And at the same time, you can do you remember what basically increase the amplitude? If you're going to like how you can increase the amplitude of the sine. So this is like the wave, right? So you can assume that this is the wave which is coming from the sound. So what I want is like I would like to discuss about the constructive waves and destructive waves. Do you remember like if the two waves are going to have the same phase and the same frequency, then when they're like together, they're going to create the constructive interference. And at the same time, if you're going to have another wave with, let's say, minus sine of x, I'm just going to write minus sine of x. Oh, why? Okay, sorry. Okay, you can see here that the this wave, the sine is moving out of phase with the first one. So when these two waves are going to like move towards together, they're going to create the destructive interference. So basically, as a sum, they're going to have simply they are going to cancel out each other. So what basically happens when we are going to have the beat is essentially we're going to get the two waves of the sound, and we're going to play one just after another one, so that the phase are going to be in like we're going to just change the phase of the two signals. So you can do this mathematically in this way. So I'm just going to put the g of x is equal to sine of x plus 1, for example. You see this? Okay, you can see here that one signal is coming just after the second one, right? Essentially the green one is coming first, or the blue one is coming first, and then the green one. So whenever we are going to put the two signals, which are coming one after another one, it is going to create something which is called the beats. So the beat is in medicine is also very important because like you can understand many things about the Hertz activity using by understanding the beat. So the thing is like this. So I'm just going to play with this. Okay, so I'm sorry, I don't remember how to create the two tones at the same time using the simulator, but I will look to this back. So essentially what I wanted to show you is to create the two waves at the same time. And if I'm just going to change the, okay, so I can do this in this way. Do you have any ideas how we can create the two signals that which are going to be played, like one just after another one? Yes.
You can open one window.
Yes, new tab.
Yeah, cool. Copy. So do you understand what's going on? Like if I just play the two sounds, like 442 here, and then 442. Also here, you basically don't see any difference, but I'm just going to change the frequency of the second one, for example. Yeah, so we can create the tones or the beats like this by just playing with the phases of the sounds or the frequencies of the sounds. We can create the beats.
Professor,
Yes,
is it happening when the waves are interfering?
yes.
So, like in the graph when they were interfering.
Yes.
Okay.
Okay, so one of the applications of the sound is using this so-called Doppler shift when we are going to measure the frequencies, right? We're going to measure the frequency of the signal which we're sending. We're going to measure the signal which we're going to receive, and by just understanding the frequency difference, we can understand whether the object is moving away or which is coming back towards the transducer or to the observer, and also its speed. So another application of the sound is when we are going to use the ultrasound in order to galvanize the gallstones, or we're going to just kill the cancer cells using the ultrasound. So if you remember in a previous lecture, we discussed about the different frequencies of the audible sound, and we say that our human ears are able to hear the sound in the range of 20 to the 20,000 hertz, and any sound which has a higher frequency than 20,000 hertz is going to be called an ultrasound. So we cannot hear the ultrasound in our ears, at least the human. There are some animals who can hear the sound as well. So we can create mechanically the sound which was a very high frequency, and this can be used in medical purposes in order to shatter the gallstones or in order to pulverize the cancerous tissues. So as a rule, in order to do this, the sound should have enough frequency, it should have enough intensity, and it should have enough amplitude to do this. So it's like all of the three physical properties of the sound should be high enough in order to shatter the gallstone or pulverize the cancerous tissues. So do you remember, like we discussed about the intensity of the sound, and we can measure this as how much pressure we're going to put into the particles of the matter, right? Depending on how much we're going to do this, we're going to measure the intensity. We're going to measure the intensity in terms of the decibels or watts per meter in the square. So if you're given a sound with the intensity 10 to the power of 3 watts per meter in the square, could you please tell me what is the intensity of the sound in terms of the decibels? In terms of the decibels. So if you remember, the formula was like, oops, I need to go back. So if you remember, the formula was like, we need to divide its intensity, 10 to the power of 3, to the 10 to the power of minus 12, right? Always we're going to divide this to the minus 12. We take the logarithm of base 10, and then we're going to multiply this to the 10. So 3 divided to the 10 to the power of 3 divided to the 10 to the power of minus 12 is going to give you what? What is the 10 to the power of 3 divided to the 10 to the power minus plus 15, right? So the logarithm of base 10 is going to just 15, right? So it's going to be log of 10 to the power of 15 multiplied to the 10. So which is going to be simply 15 multiplied to the 10. It's going to be 150 decibels. So decibels. At the same time, this intensity 10 to the power of 5 is going to be corresponding to the 170 decibels. So in order to just give you some impression is that whenever we're going to have a lecture in the big room, so the intensity of all of the sound altogether in this room is going to be about like 80 decibels. When you're going to play a loud sound, it's going to be about 90 decibels. Like, so in a loud environment, the intensity of the sound is about like 70 to the 90 decibels. And you can imagine that 150 decibels, it's like a huge intensity of the sound. So if you're going to use the huge frequency, huge intensity, and also huge amplitude of the sound, it is possible to shatter the gallstones. And it basically uses the mechanism as how it is going to kill the individual cells is that it is going to alter the permeability of the sounds through something which is called the cavitation. So the cavitation is the creation of the vapor cavities in the fluid. So at the same time, the longitudinal vibrations of the sound and the ultrasound of the sound so are going to alternatively compress and expand, and at the sufficient amplitudes, at the sufficient intensity and the frequencies, it is going to separate the molecules. So this is how the cells, individual cells, are going to be killed. So the idea is at the certain intensities, the sound is going to essentially expand and compress the particles of the medium. So this is how it is going to kill the cells. So this is one of the examples how the ultrasound can be used in the medical purposes, essentially in the surgeries. The tip of the small probe oscillates at the frequency of the 23 kilohertz, which is like 23,000 hertz, which with such a large amplitude that it pulverizes the tissue on contact. So this is one of the applications of the ultrasound. So another application of the ultrasound is used in order to get the signal or the images. So you probably have gone through something which is called UZI or something like this. Have you heard about this? Like it's ultrasound imaging. When we are going to get the images of the tissues or the bones or the liquids, using the sound, using the essential ultrasound, using the sound with the intensity higher than 20,000 hertz. So the idea of how it works is that we're going to have the transducer, which basically is going to create some sound. It's going to create the sound in this way. So it's going to create some pressure around itself on the air, and it's going to create the ultrasound. At the same time, it is possible that it receives some signal and convert this into the electric signal, and it basically measures the frequency of the sound and also its intensity. So it's very important that we're going to use the intensity of the sound in order to differentiate between the two different materials which we're going to have. So essentially the idea is like this. So if the transducer is able to produce some signal, it's going to send the signal into some object. Whenever the signal is hit by this object, it's going to be transmitted, or some portion is going to be transmitted. And by just understanding how much time it took for the signal to reach the object and came back to the transducer, we can understand what is the distance between the transducer and the object. Okay, so the idea is like this. I can understand what is going to be the distance between the observer and the source of the signal, or between the object, which is steady, which is not moving, by just measuring the time and knowing the velocity. So we've seen previously that the velocity, the speed of the sound in the tissue is 1,540 meters per second, right? Let's assume that it took about 2 milliseconds. Does it make sense? Whatever. 2 milliseconds, the signal goes to the object and came back from the object. It took 2 milliseconds. Could you please tell me what is the distance between the transducer and the object? You remember how we calculate the distance? The distance is always equal to the velocity times the speed times the time. Right? And then from here, we can get that it's going to be 1,540 meters per second. 2 milliseconds is 2 times 10 to the power of minus 3 second. And if you're going to multiply this, what you're going to get is, you're going to get a huge distance, right? Well, let's make this 2 nanoseconds. Is it okay if I make this 2 nanoseconds? Then this is going to be equal to 1,540 multiplied to the 2 divided to the 1 million. It's going to be 0.00308 meters. And if you convert this into the centimeters, it's going to be 0.3 centimeters. Okay, which makes sense. Yes.
if it's nanosecond, wouldn't be 10 in the power of minus 9?
Oh yeah. Let's make it 2 times 10 to the power of minus 6 seconds.
Okay.
Okay. So I just wanted to show you the idea is that by just knowing the speed of the sound and by just knowing the time, how much it took to go the signal from the source until the object can come back, we can understand what is going to be the distance. But essentially, this is the double of the distance, by the way, right? It is the signal go to the until the object and comes back from the object. So that's why the actual distance between the source and the object is going to be equal to 0.15 centimeters. Okay. So have you ever seen the graph of the ultrasound? So I'm just going to show you here. So maybe this kind of stuff without the colors. So sometimes we're going to see this was the gray and black image, like the gray and black image. So it basically is going to differentiate the colors depending on the meta as well, right? So what I want to understand is how the ultrasound or how the signal of the sound can be used in order to differentiate the matter. So the idea is very similar to the X-ray. So do you remember how it works in the X-ray? So we did a couple of so in the X-ray it was like this. So you're going to send some signal like of the electromagnetic wave, and some of the objects are going to absorb some portion of this. So that's why in the detector you're going to simply have less signal, and the places when you're going to have those objects, for example, the electromagnetic wave is going to go through in between of the fingers, and your fingers are going to absorb some portion of the signal. So that's why you're going to have the thick picture of the fingers. At the same time, the similar idea is used in the sound. So essentially, there was something which is called the acoustic impedance, and depending on the different values of the acoustic impedance, the portion of the signal which is going to be transmitted from the different materials, it appears can be different. So let's discuss about something which is called acoustic impedance. That is one of the properties of the sound again. So far we discussed about the intensity of the sound, right? We discussed about the speed of the sound. We discussed about the frequency of the wavelengths of the sound. And the acoustic impedance of the sound is one of, again, the properties, which basically the resistance of the medium to bring its particles into the motion. So the higher the acoustic impedance, the higher the resistance of the medium. So more efforts we need to put in order to make the sound, in order to move the particles of the medium. So the acoustic impedance essentially is multiplication of the speed of the sound in the medium to the density. And you can see here that, so for the air, it's relatively small value. It's going to be just 1.3 kilograms per meter in a cube, which is the density of the air, multiplied to the speed of the sound in the air, which is like 331 meters per second, and you're going to get roughly 430 meters, so kilograms divided to the meter square seconds. But for the volta, it's going to be much more higher value. It's going to be 1.5 millions. So like as a rule, we're going to measure this in reals, so something which is called the real. So we're going to denote this as Z. So it's going to be for the volta, the acoustic impedance is about 1.5 megareals. So I can explain you this, and it was an example of you are going to make the sound in the air, or so how difficult it is for you to make the sound underneath the water. So if you are, for example, swimming, so you went into the water and you would like to make some sound, and you can imagine that it's superbly difficult to create the wave of the sound underneath the water than in the air. So this is what does it mean, the acoustic impedance. So it is how much effort you need to put in order to create the sound. So obviously in the water, you need to put more efforts to create the wave of the sound. So the reason why we're talking about is that, so depending on the value of the acoustic impedance, so the portion of the signal which is going to be transmitted back to the transducer can be different again. So if you have got some like the liquid, for example, around the tissue, okay, tissue, and if the signal, which is like I'm sending, so it's going to be some liquid, some water. So if you're going to send some signal to the water, so let's say like 10% of the signal is going to be come back from the water, and if I'm just going to send a signal to the tissue, maybe only 3% of the signal can come back. 10% comes back, and if I'm sending this to the tissue, and then 3% is going to come back, and by just knowing how much signal came back to the transducer, I can differentiate the two different methods. So that's why I can get the gray and black colors in my ultrasound screening. So we are going to calculate the amount of the signal which is going to come back by just knowing the acoustic impedance of the two different matters. So let's assume that the signal is going back from the air to the water. For example, it is, you put some like transducer to your skin. So the signal is going to go back from the air to the water, to some liquid. And then the Z1 is going to be the acoustic impedance of the air. Z2 is going to be the acoustic impedance of the water. And by just substituting everything here to this formula, you can understand how much of the signal is going to be transmitted from the water. So you're sending like 10 signals, for example, then how many of them is going to come back? Okay, so let's do the example. So calculate the intensity of the reflection coefficient of the ultrasound, which is going from the fat to the muscle, from the fat to the muscle. So I'm just going to put down the formula again, and then we're going to work out with this formula a bit. So the alpha is going to be equal to the Z2 minus Z1 in the square, divided to the Z1 plus Z2 in the square. Okay, so when it goes back from the fat to the muscle, so the acoustic impedance of the fat Z1 is going to be equal to the 1.34 megareals, it's 10 to the power of 6, and Z2, the acoustic impedance of the muscle in average. So there are like different values for the different muscles, but in average it's about 1.7 times 10 to the power of 6 reals. And then I'm just going to put everything together and calculate the alpha. So the alpha is going to be equal to the 1.34 minus 1.7 in the square, divided to the 1.34 plus 1.7 in the square. So let's calculate this together. 1.34 plus 1.34 minus.
I'm sorry, Professor, did you not mix
Yes.
Z1 with Z2?
I didn't, but it doesn't matter.
It doesn't matter? Yeah, sure.
It doesn't
sure.
matter. I mean, you score them anyway. Okay.
Yeah, right. Thanks.
0.1296 divided to, say, 1.34 plus 1.7 in the square is going to be 9.2416. I'm just going to take its reciprocal and multiply this to the 0.1296. It's going to be 0.014. So if you are going to convert this into the percentage, it's going to be 1.4%. It means that only 1.4% of the signal is going to be transmitted from the muscle tissue if it goes away from the fat. Okay, so by just understanding how much of the signal came back from the different objects, we can understand what is this object. So if you're going to put, for example, the signal again, you're sending from the air to the water, some portion of the signal is going to come back. If you're going to send this to the fat, less portion of the signal is going to come back from the fat. So that's why we are going to have the different colors in the ultrasound screening. Well, okay, so this is what I wanted to discuss with you so far for today. If you have any questions, I'm open to discuss it. Also, in the previous group, people asked me how they can reach me. So as a rule, like next week, we're not going to have anything new. We're like all of the 3 lectures is going to be about the review of our previous topics, or we're going to go through some of the quizzes and solve them together. And at the same time, I'm in the office like most of the time during the day, so you can just text me. So when you can come, and I will just like, if I'm just going to be in the office, I will answer you. Okay.
Professor, can you upload the video to Classroom?
Yes, so this video I will upload to the Classroom. Okay, thank you very much. Have a nice weekend.
Professor?
Thanks. Yes.
Will we have mock exam like in midterm?
Yeah, if you want, I can do this. Like, but all of your quizzes actually are coming from the final exam of the previous year.
Okay, thank you. Have a nice day.
Okay, bye.